Swayam Prabha. Digital India. Educated India.
So we will like to sum up the lecture with the governing equation which will form the basis to address a variety of diffusion problems. So if you recall, we said total diffusion flux, total flux as observed by a stationary observer Na will have two components. One is the bulk transport. Of course, you can write this flux same as VA CA, where VA is the molar velocity of the component A. This will also equal to XAN. The first component is bulk transport, and the second component is your molecular diffusion. And we can write XA as, which is the mole fractions, as CA over CA plus CB. And J we can write as we defined earlier. This is nothing but CA UA minus U bar. So this is the molar flux of diffusion by Fick's law as observed by the observer who is moving with this average bulk fluid velocity. This will equal to minus D AB del of CA over del of Z. So negative sign, all it means diffusion takes place from higher concentration to lower concentration. So CA1 is greater than CA2. So if we add it here, this Na, right, substitute all these equations, this term becomes Na Ca over Ca plus Cb. So this is a term for mole fractions, and we have Na, which is Na plus Nb minus Dab del Ca over del Z. So we can box this equation as our governing equation for diffusion. Governing equation for diffusion. And you will see that this equation is a governing equation to address several very common situations of diffusion in a stagnant or in equimolar counter diffusion cases. There are several such examples which in which cases can solve for the concentration profiles starting from these equations. The main idea is that Na has two components. One is the bulk transport, the first component, and the second component is your molecular diffusion by Fick's first law. Okay, we would also like to revisit continuity or species balance, which you may have done in earlier lectures or earlier class or in some other different course. So let's revisit species balance. And continuity. So continuity is nothing but total material balance or total mass balance. Okay, and what we do here is we will take a differential elements of del x, del y, del z or dv, and we'll make a well-known species balance, and we will see that how does it relate to what we have obtained just now. Okay, so if we choose a control volume of del x of del v volume, which is del x into del y del z, and we assume there is a fluid flow of a binary mixtures of A plus B. We assume for our simplicity it's a constant mass density or constant molar density fluid. So kg per cubic meter and moles per cubic meter, it's a constant. We have A plus B, and if you write down species balance, if you recall, we have del Ca over del T plus del dot Na minus Ra equal to 0. So we have unsteady state term, we have total flux and if you recall, this has two components. One was bulk transport and the second was diffusion flux, and this is a reaction term. So essentially we are looking for moles in 1 cubic meter volume in 1 second. How does the moles changes in 1 second in 1 cubic meter of the control volume? And if we assume that there is no reaction, then RA equal to 0, and we substitute Na from our previous equations which we had, where we said that Na has two components. One is the VCA, bulk transport, plus, and the second component is your molecular diffusion. If we substitute here, we get del Ca over del T plus V bar dot del Ca equals DAB del square Ca over del Z square. So this is our species balance for A in this control volume of del X, del Y and del Z. The first term is the unsteady state term, the second term is your transport by convections, by bulk transport, and this term is your molecular diffusion term. Okay. This term can also be written if we write down the similar expressions. What we wrote or what we obtained just now, that's a change in the concentration as observed by the stationary observer. But if the observer also moves with the bulk transport or with the average molar velocity, we have the same term, same equations written as dCA over dt equals DAB del square Ca over del Z square. So we have a substantial derivative here. So this is the rate of change of concentrations, rate of change in concentration as seen by the observer moving with the average or the fluid average velocity. So this is again, it's consistent with what we had seen earlier, that the observer, if he moves with the bulk transport average velocity, all he will see is a diffusion flux. On the other hand, if the observer is stationary, he will see two terms here. One is with due to the bulk transport and one is with this molecular diffusion. Okay. We can also write down the similar balance for the component dB, which would be del Cb by del T plus V dot del Cb equals DAB del square Cb over del Z square. And if we add the two equations, we get del C over del T plus V dot del C equals 0. Because we have J plus JB equal to 0, we are assuming that C bar is a constant. If we write in terms of mass average mass concentrations, we can write the same equation del rho over del T plus V dot del rho equal to 0, where we can substitute V with V star, where V star is mass average velocity, defined as very similar to how we define V bar for molar average velocity. This would be rho A VA plus rho B VB over rho A plus rho B. And this equation is well known continuity equation. All right. So now what we do, we have obtained a very simple equations for molar diffusion flux Na, and we have also obtained an equations in terms of differential control volume or differential species balance continuity as well. We will like to apply these different equations for different situations, or very simple or well known well used equations situations, case 1, case 2, case 3, etc. So we start with case 1 as an example where we can apply the equations which we have obtained so far. Let's assume we have a state, we are assuming a steady state. We have binary mixtures of A plus B. There is no chemical reaction are equal to 0. We also assume the pressure and temperature is a constant. So we essentially we are looking at Cartesian coordinates, diffusion between 1 and 2, Z is the directions, and A diffuses, A and B, we have the diffusion for, let's assume that there is a concentration gradient for A and there is a concentration gradient for B. Okay. So under these conditions, if you assume that it's a steady state, there is no chemical reactions. All it means that molar diffusion flux of Na and Nb, they are not function of time, and since there is no chemical reactions and we have this Cartesian coordinates, since per meter square of area for, so we have essentially Na and Nb, they also do not change with z directions, because moles per second as well as moles per second per meter square are conserved in the z directions. So we go back to our previous equations, or what we obtained for Na in terms of bulk transport, Na plus Nb into mole fractions, which we can write as Ca over C minus dAb del or dCa over dz. So we are assuming 1D diffusion flux here. Okay, and this equation can also be arranged and integrated. Since Na and Nb, they do not change along the z directions, we can integrate from Ca1 to Ca2, or between 1 and 2, with dCa over Na minus, or NSC, excuse me, minus Ca Na plus Nb equals 1 over C dAb dz from z1 to z2. So now we can integrate, since C is a constant, Na, Nb diffusion flux are also constant because of a steady state, and as well as we are assuming that there is no reaction, so the molar flux is also constant at any plane between 1 and 2. Okay. So now on integration of this equation, it's not difficult to obtain an expression for Na in terms of the quantities like Nb, diffusion coefficients, Z, distance between the two planes, and concentrations. It's very easy to obtain an expression for Na, a general expression for Na in terms of Na. We have Nb dAb C over Z ln Na over Na plus Nb minus Ca2 over C Na over Na plus Nb minus Ca1 over C. So this is a general expression we have obtained for diffusion flux of A, but if you see it carefully, there is a term here Nb. So even if these quantities like diffusion coefficients dAb C, which equals P over RT, Z, diffusion length, they are known, and we know the concentrations at the two planes Ca1 and C2, we cannot solve for Na in terms of these quantities because Nb is also unknown. Which means we must look for a relation between, Na and Nb. Okay. All it means that we have to take some special cases in which we can have one more independent equations to solve for Na. So one of the example would be that if we have the same 1 and 2 planes for A to diffuse in the z directions, we assume that if we assume that A is getting decomposed into B and some other compounds. So we can take an example of, say, methane, which is A decomposes into carbon and hydrogen. So the surface is acting as a catalyst. In other words, there is no homogeneous reactions inside the plane, inside these two planes. So RH is still 0, but when A reaches the plane 2, it gets decomposed by some catalytic reactions into carbon and hydrogen diffuses in the opposite directions. Okay. So in this case, if you look at the stoichiometries, if you recall, we said that one of the prerequisite is stoichiometry. In this case, we can say that Na and Nb, they are related with due to their stoichiometric ratios. So we have one more equation, essentially Nb in terms of Na, and now we can go back and substitute Nb in terms of Na to obtain a relation for molar diffusion flux of A in terms of all the unknown quantities which we have. So if Nb equals minus 2 of Na, then we can write Na over Na plus Nb equals minus 1, and therefore we have a relation for Na minus dAb C over Z ln 1 plus Ya2 over 1 plus Ya1. So all we are trying to say here that we have obtained relations for a special case in which we can predict how much is this moles per second per meter square of your diffusion plane in terms of diffusion coefficients, concentrations, bulk total concentrations, Z, and mole fractions of 1 and mole fractions of A at planes 1 and 2. So mole fractions Y will be the same as Ca over total concentrations, or if it's a gas, we can write in terms of partial pressure of A and the total pressure. Okay, so all we have done that we have obtained these relations for Na in terms of the unknown quantities. We will take another example, case 2, in which case we have steady state diffusion. Steady state diffusion of A through stagnant B. So when we say it's a stagnant B, we have Nb equals 0. And an example, a very common example would be if you have water and air and ammonia. So we can assume that air is insoluble in water and ammonia is soluble. So it will diffuse and will get solubilized in water. We also assume that water does not evaporate for our simplicity. There is no chemical reactions, R equal to 0. We assume steady state. So all the diffusion flux which we have Na and B, they don't change with time, nor do they change with Z. So we can have the axis here with Z from 0 to some height. So all we will do now, we will go back to the same equations, start from the governing equation which we had obtained here, and we try to see how we can simplify here. So we have, if we go back to the same equations, Na equals mole fractions Xa, Na plus Nb, but Nb is 0 because air is stagnant, minus dAb dCa over dZ, and Xa we can write in terms of partial pressure of A and the total pressures. So we have Pa by Pa, Na minus dAb by RT. We can apply ideal gas law to make it dPa over dZ. So all we have said, Ca equals concentration of A equal to Pa over RT, applying ideal gas law, and P we can write as sum of the two partial pressures Pa plus Pb. So now we have obtained a relation between Na and this partial pressure gradient. But since a steady state, Na does not change with time, nor Na changes along the direction of Z. There is no chemical reaction here. So we can easily integrate these equations, which is independent of Z, to obtain Na equal to dAb Pt over RTZ ln Pt minus Pa2 over Pt minus Pa1. So in this case 2, when B is a stagnant, we have obtained a relation for diffusion flux of Na in terms of the known quantities, partial pressure of A at 1 and 2 and the diffusion length. More important here is to understand how does the profile will change between the two planes. So look at this. If we have this water and air interface, it's ammonia which is diffuses inside. So ammonia is soluble, and this will have a concentration gradient for ammonia to diffuse here, but air is insoluble, right? So air is insoluble, and one can also write down, express Na and Nb both in terms of molar diffusion flux as well as the bulk transport. Important here to note that since air is insoluble in water, there is bulk molar convections or bulk molar transport induced because of ammonia diffusion. Since Nb is 0, which means V Cb, so the bulk transport of B of air has to be equal to the molar diffusion flux of air. In other words, any stationary observer, he will observe that B is 0, but if this guy moves with this average velocity of at u bar, he will see that there is a diffusion flux given by DAB, DCB, DZ. This principle of one medium diffusing when the other component is stagnant is applied very frequently in case of a very so-called example known as stiffened tube. So what we did here, that we started with the same equations and we solved for case 2, where we say that A is diffusing but B is stagnant, Nb is 0. So when we say that B is stagnant, total molar flux of B is 0. That doesn't mean that B doesn't have, if an observer moves with this convective or V velocity, he will see air diffusion by this Fick's first law. But to the extent that molar diffusion flux of B will be counterbalanced by the bulk transport of B. All right. So this principle is very frequently applied in obtaining or predicting the diffusion coefficients in well-known stiffened tube. So we will take this example of stiffened tube, which is very simple tube geometry configurations to measure or to predict binary diffusion coefficients. So essentially we have a U tube, and say we want to measure or we want to predict or estimate a vapor of an organic compound, say acetone, in air. So we have a tube like this in which air moves very gently on top of this. So when the acetone evaporates, it has a diffusion length of del z or some height h before it's carried by this air stream outside. We can assume that air quantity is very large to the extent that the concentration of acetone Ca2 is 0, or mole fraction of 2 is 0 at this location 2. At location 1, the interface of acetone and air, we can write Y mole fractions of A at location 1, A is here is acetone, as vapor pressure at that temperature and the total pressure P0 over P. Again, we assume that air is not soluble in this organic, and with this technique one can obtain this. We can predict the diffusion coefficients of acetone in air. If you look at carefully, as acetone evaporates, its level is going to come down. So if you start with this locations at some location t equal to 0, after some time acetone will evaporate and its level will get down to some level t equal to t1 from Z1 to Z2. In other words, it's an unsteady state problem because the level of acetone continuously keeps on decreasing. So if the level of acetone decreases, or Z, right, if we put the axis here, if Z decreases from some level Z1 to Z2, it's an unsteady state problem. We cannot apply what we obtain for diffusion flux of A in terms of your bulk transport and your diffusion flux. molar diffusion flux, because every time in all the two cases which we had earlier, we assume that Na, it's a steady state, Na does not change with time, and Na does not change along the z directions. But since the level of acetone decreases, it's an unsteady state problem. But still, the more important here to note is that the level of this acetone decreases very slowly. In other words, we can assume what do we call pseudo steady state approximations, which means, or this also known as quasi steady state approximations. In other words, in this case, since the level of acetone decreases very slowly, we can assume that over the time period of diffusion flux, the level of acetone is almost constant. That's a pseudo steady state approximation. In chemical engineering or in so many contexts, you will be seeing that we make this kind of approximations. Whenever we have two rates and one rate is much larger than the other rate, one can apply this quasi steady state. So here, level of acetone decreases very slowly. Maybe when you do this experiment in your lab, you will see that it takes almost like 8 to 10 hours, if not 24 hours, before you see a measurable difference in the height. Okay, so assuming that it's a quasi steady state, we can still apply the previous equations. Air is insoluble, so we can say that Nb, which is air, is 0, and we can apply the previous equations directly there. Na, which we wrote as d AB Pt over Rtz ln Pt minus partial pressure of A at locations 2 over Pt minus Pa1. Okay, Pa1, as we said that Pa2 we can assume to be 0, because as soon as the acetone gets into this stream, we can assume that it's swept by this air. Partial pressure of A1 we can write as vapor pressure of acetone at this temperature. Okay, so this equation, except that we should be able to make a material balance. So let's assume that the level decreases from Z1 to Z2 over a time period of T. Okay, so if Na is the diffusion flux of Na into cross-sectional area, so this would be the cross-sectional area, into del T, this will become your moles. So over del T, so much moles of A has diffused, and this is nothing but how much material has evaporated. So we have del Z, this is your del Z, into cross-sectional area, that will make it volume, into rho A, that the density, divided by Ma. So all we have done, we have made a material balance, and we can substitute this Na here. We can integrate now this dZz over this del Z to obtain this relations dAb RT. If it's just simple substitution, Pt over Z ln Pt, Pa2 we can assume 0, Pt minus vapor pressures equal to rho A over Ma. We have dz over dt. So del Z, del T, we take the limit del T tends to 0. We have obtained this relation. We substituted Na from here. Now we can integrate Z, dz and dt here to obtain or to predict diffusion coefficients in terms of all known quantities, which is rho A over Ma, RT over Pt. We have ln Pt minus Pa1 over Pt minus Pa2 Z2 square minus Z1 square over 2 into 1 over total time. So we have this dt, we integrate this dt. So knowing all these quantities, actually we said that P1 is 0, so we can delete this term. We have Pt minus P, excuse me, so Pt minus P0. So now one can get an estimate of diffusion coefficients of acetone in air. So all this in Stephen diffusion, we made an approximation on that there is a quasi steady state, and the rate of fall of acetone vapor in air, in the tube is very small. So Na and B, both of them remain constant with the time as well as along this length z, and then we integrated these equations to obtain the quantities for diffusion coefficients, which we can be obtain in terms in the quantities meters squared per second for acetone in air. Now we will take one more example to apply what we have done in earlier. So this would be the case 3, and this is a simple example, but it's called steady state. So we have steady state equimolar counter diffusion. In other words, we have Na equals minus Nb, and which is a constant with time. In other words, n equal to 0. So there is no bulk transport. There is no bulk transport. And if you put the same equation, same n equal to 0, and simplify, we have Na equals minus dAb over RT d PA over dz. And then one can integrate this to get an expression for Na equals dAb RT z PA1 minus PA2. So essentially we have total pressure. Here we are saying that Pt is constant, and there is a gradient of PA from PA1 to PA2, and there is a gradient of B from PB2 to PB1. The total pressure P is sum of the two partial pressure P and PB. Okay, so these are the examples which we took. We took 3 examples: case 1, case 2, case 3, where we have shown that we can solve for diffusion flux, or we can predict the diffusion flux. And one of the example we had applied in case of Stephen tube, which is widely used to predict or estimate diffusion coefficients of one species, vapor species, diffusing in other species like DAB, etc. If you look at carefully these equations, Fick's first law, we wrote J equals minus DAB dC over dz. So this unit of J is moles per second per meter square, Ca is moles per cubic meter, and we have meter square per second. Okay. Of course, there are experimental methods to measure DAB, or there are so many models to predict this DAB. In general, for gases, one correlation is quite very popular, given by Wilke and Lee, which we must know at least that diffusivity, binary diffusivity, is proportional to 1 over Ma plus 1 over MeB. All it depends upon, all it means that lighter molecules will have larger diffusivity, heavier molecules will have a smaller diffusivity. It's a temperature dependent to the power 3/2, 1 over total pressures, and it also depends upon the size of the molecules. In other words, RAB is nothing but the average radius of two molecules, Ra and Rb/2. So at least we should remember that it has a strong temperature dependence, T to the power 3/2, and it's 1 over pressures. Diffusion for liquids are also, there are so many correlations available to estimate. For the liquids, the one for dilute solutions, we should know that 0 signifies here for a dilute liquids or solutions. It's a molecular weight to the power half P over viscosity. So here it's T to the power 3/2. For the liquids, it's linearly proportional to temperatures. And whatever equations we obtain for the gases, we can equally write for the liquids, except instead of partial pressure which we use for the gases, we can write in terms of concentrations. In other words, we can write Ca as PA over RT. Mole fractions we can write as Ca over Ca plus Cb. So for the liquid we use the nomenclatures. Xa for the gas we use Xb. Total average liquid concentration or solution concentration can also be written as C equal to rho over m average density. So we just take the case 3 for our simplicity. If we write down the same, if we obtain the same, we want to obtain the similar expression for the case of liquid, then we can write Na as dAb over Z as Ca1 minus Ca2. So instead of partial pressure of A and 2 of A at 1 and 2 for the gases, we are substituting with the concentrations of Caz minus Caz2. We can also write this as dAb over Z and rho by m average as average concentrations, liquid concentrations, and we can write in terms of mole fractions of A in liquids at location 1 and 2. So similar equation can be obtained for all the two cases which we did earlier, case 1, case 2 and case 3. All right. Now before we end this lecture, we should also, what we did obtain so far, those cases of 1, 2 and 3 we had rectangular coordinates, in which case when A or B diffuses, then the planes are rectangular planes, and these plane area of this plane, they do not change with the distance set. But we can have several common examples of spherical geometries or cylindrical geometries where the area changes as you go along this r directions. So we have 4 pi r1 square, 4 pi r2 square, or in case of cylinder we will have 2 pi r1l, 2 pi r2l. So in these cases, what happens when we say that there is a steady state, it's a moles per second which is constant. Moles per second per meter square of the diffusion plane will change. Unlike in case of the Cartesian coordinates, when we say that is a steady state, moles per second as well as moles per second per meter square, both are constant. So all we have to do is that to go back, start with the same equations for Na in terms of bulk transport or diffusion flux, except when we integrate, we have to be careful that r changes in the area changes in terms of r, and it's a moles per second which is constant, not moles per second per meter square. And it's a very common example in case of evaporation of a naphthalene ball. If you have a naphthalene ball or some Casper spherical ball, and if it evaporates in a stagnant air, its size will change with time. The way we have seen in case of Stephan tubes. When we took the Stephan tubes, we had the surface of acetone. When it evaporates, the level of acetone decreases, but still we have a Cartesian coordinate system. The cross-sectional area does not change with time. But in case of a spherical ball or like naphthalene ball, we said when it evaporates, the size will change, or when A evaporates into stagnant medium, then we are encountering different planes of different radius. Okay, so we'll take this example for spherical geometries. Okay, so essentially now we have diffusion in spherical coordinate. Okay, and we still we have similar restrictions. It's a steady state. There is no reaction. So when we say steady state, actually it's a moles per second which is constant. So all we are saying that a steady state, Na and Nb both will be a function of r or z, although it's a steady state. Why? Because if we look at different planes, then we have, if A diffuses like this, on the surface area or the diffusion plane area will change from 4 pi r1 square to 4 pi r2 square. Okay, in other words, Na, which is moles per second per meter square into 4 pi r square, this will be conserved, this will be constant. So what is constant here in case of spherical coordinate is moles per second and not moles per second per meter square. Similarly, if we have cylindrical coordinates, then we are trying to say that is Na into 2 pi r, that's a constant. in case of this is cylindrical coordinates, and if we have a Cartesian coordinates, which we did earlier, it's Na which is constant. Okay, so it's very important that we understand that it's moles per second, or if we multiply by the density, then kg per second is conserved, not moles per second, not moles per second per meter square. Okay, so now we take the similar expressions and we substitute in the previously what we have obtained in case of for Na in terms of bulk transport and diffusion flux. So we say that Wa, if we define a quantities, which is kg per second, then this is Na into 4 pi r square into rho a, where rho is the density and r varies between r2 and r1. And now we have the expressions for Na. Now it's a function of r or z equals mole fractions Ya into n minus d diffusivity dCA over dr. So it's the same expression, except we realize that Na is a function of r, and Na is not constant. Na is not, although it's a function of steady state, it's not a function of time, but Na changes with r. So we have W dot r Na 4 pi r square into rho a, and we are writing starting from the same equations which we had earlier, NAR equal to YN bulk transport and this diffusion flux. So if we substitute here, or we multiply these equations with 4 pi r square into Na equals 4 pi r square Ya, Na equals Na plus Nb minus d dCA over dr. So if you go back to the same case where we say that Nb is 0, very special case which we had earlier, that diffusion medium A diffuses but B is stagnant. So it's a similar case, except now we are in the spherical coordinates and we have a steady state. So kg per second is conserved, Na into 4 pi r square and W is constant. So now we can substitute, we make it Nb equal to 0. We can substitute this equation here to obtain W dot into, or W dot P minus PA over P equals minus D over RT dPA over dr 4 pi r square. So all we have done, we have made Nb equal to 0 and we have substituted 4 pi r square Na as W dot, and W dot is constant, is a kg per second, it's conserved here, equal to minus 4 pi r square. Now we can integrate. So if we integrate W dot RT over 4 pi P TAB, integration from R1 to R2 dr over r square equal to PA1 PA2 dPA over P minus P. The small p is same as the partial pressure, so let's use on the same nomenclatures dPA P minus P. Okay, and so essentially by integrating from R1 to R2, this is Na, and we realize that at any location R, the diffusion area is 4 pi r square, which varies from 4 pi r1 square to 4 pi r1 r2 square, and we have partial pressures PA1 and PA2. So now we can integrate to obtain equations for W dot RT 4 pi P DAB 1 over R1 minus 1 over R2 equals ln total pressure minus PA2 over P minus PA. Okay, so this is an example which we have taken here for diffusion of A in a stagnant B where we have a spherical coordinates. So it's a very similar to a naphthalene ball, we have a sphere, and this sphere evaporates in air, which is a stagnant. And if you compare this, what we had earlier, we had a stiffened tube, acetone filled with acetone, and acetone evaporates. In this case, when the acetone evaporates, then all the diffusion area is a constant. In case of naphthalene ball or naphthalene vapor, when it diffuses in air, then area changes from 4 pi r1 square to 4 pi r2 square, etc. In which case, it's a moles per second which is conserved, not moles per second per meter square in case of spherical coordinates. Unlike in the Cartesian coordinates, both moles per second and moles per second per meter square is conserved. So these are the three examples we have taken in today's lecture: case 1, case 2, case 3, mostly for Cartesian coordinates, and one example we have seen for spherical coordinates.